This video is on doing curve fitting in Excel for Physics 151 Lab, supplementing the written instructions. Here I have a spreadsheet where I have pasted in the table that is in the written document, the curve fitting document. I will erase a lot of what's here because it just shows the numbers and not the formulas you need to enter. So you can follow along, go to the written document, copy that table and then paste it into a spreadsheet and then follow along. You will have a chance to do this with your own data later. Okay, so I'm going to erase these numbers because we will set them later. I'm going to erase the numbers for the fit function because they are just numbers. The formula is not there. I'm going to erase the chi-squared because those are just numbers. The formula is not there. So presumably you have taken pairs of data points x and y, and we have 10 pairs and there's an uncertainty in y. And the goal is to find the function of f of x that best describes the data y. Of course, you should always start with a graph. Select the data, insert, go to a scatter plot, and we just plot the points. And that gives you a visual of what things look like. As I said in the previous video, there is a trend line feature within Excel. Right click, add trend line. The straight line does not look very good, but if you add a polynomial, then yeah, that looks okay. But the problem is it's a little limited in the types of functions it can produce fits for. And even if you put the equation and the r squared on the chart, it can give you the parameters for the function that best fits, in this case a second degree polynomial, 3 parameters, here, here, and here. It gives you a number called r squared, which in some way indicates how good the fit is. 1 is good, 0 is bad. One thing it does not tell you is what are the uncertainties of these parameters. In physics, when we fit data to some function, the parameters of that function usually have some physical meaning. For instance, they might refer to gravitational acceleration, or they might refer to mass of a particular object. So we do want to know those uncertainties. So let's remove the fit. Delete trend line. So we need a function. And in the written document, it discusses a function that has an x squared and an x term, but no constant term. Perhaps it is some situation where for some physical reason the constant term would not be there, it would be 0. So the first step is to start typing in the function equals. Now we want to multiply by x squared. Okay, in this case, x is over here in x5, so x asterisk x. Whoops. Let's try that again. X asterisk. Okay. Start over. Equals. Click on where the x is, x5. Type in asterisk. Click on a5 again. Now this gives us the x squared, but it doesn't give us a coefficient multiplying it. So we can multiply it by some coefficient. Now that coefficient needs to be stored in a particular place. So if we call that coefficient little a, and it can be stored in cell B1. To make sure that we always refer to B1 when we copy the formula later, we'll use the $sign $B, $1, and then an asterisk. And that does a calculation, which so far is 0 because everything is 0. I'll click back up there because we also need to add the linear term. So plus, and now the coefficient of the linear term will be little b, which is in cell B2. So $B, $2, asterisk, and then cell A5 again. Right, that needs to be a B2. Okay, so now the formula is showing the coefficient A in cell B1 times A5, which is X, times A5, which is X, plus the coefficient, which is in B2, called little b, times A5, which is X again. If I copy this down, we can look at one of them and see that when I copied it down, the reference to the X column got changed, so now it's referring to cell A10, which is the proper X for this row. But the coefficients stored in B1 and B2, it's still referring to those where they belong. Okay, so again, nothing there because we haven't put any numbers, but it's always a good idea to plot the fit on the same graph as the actual data so you can compare the two. So if I right click on the graph, select data, and I can add a series. I will name this series the, say, theory fit. Click down here with X values. It will have the X values in column A. And for the Y values, I'll select column C. While I'm at it, I'm going to edit series 1 and change its name to data. And it says OK. Okay, one thing I want to do is add a legend so I know what is what. So click here, that will add a chart elements. I want to add a legend, and it gives me the legend I want. The third thing I do is, since this theory fit is an actual function, a continuous function, it helps a little if it's a line instead of a bunch of dots. So I'll right click on that, format data series, and select a line. And the other thing I want to do is get rid of the marker dots. Okay, so we're seeing a line now that corresponds to the fit function. There's nothing there at the moment because my parameters are both 0. So we can eyeball this to see what, for instance, the x squared parameter would be at x equals 10. X squared is 100. And to get 60 out of 100, we want to multiply by 0.6. So I will just eyeball A as being 0.6. And see, it's a not unreasonable fit. Some places it's above, some places a little below, so it's at least to some extent matching the eyeball fit. It doesn't look wildly wrong. We could eyeball B as well, but at this point I'd just be kind of guessing because it looks like it's as much. Maybe I need to bring it down a little because there are more points below than there are above. If I need to bring it down, say 2, then to get 2 out of 10 I need to multiply by 0.2, and I want to bring it down so it's negative. So it brought it down a little. Okay, but that's so far just an eyeball fit. To numerically determine when we have the best fit, we do the chi-squared. So I'll go to cell E5. Chi-squared is a calculation, so equal. And to do the calculation, I'll put a couple parentheses here because I'm going to need them. You take the difference between the data minus the function. So I take the data minus the function, take the difference between them, close parentheses, then I divide that by the uncertainty. Close parentheses again, and I'm going to do one more thing. But first, this is telling me how much the fit differs from the data in relation to the uncertainty. So how many times bigger than the uncertainty is the fit off from the data? So here the fit is off by a certain amount. Here it's off by a small amount. I haven't plotted the error bars, but they would be pretty small on here. We probably wouldn't even see them. So here the chi-squared would be small. Here it's going to be bigger. Statistically, it's found that when you do this, you also want to square this quantity. So caret 2 will square it. And that is the chi-squared. For this data point, the chi-squared is 0 because it's right on. If I go down 1, drag it down just once, then the chi-squared is 1.5. So they're different by about 0.12. That gets divided by 0.1, so we get 1.2, and then that's squared, about 1.5. So I can drag this down all the way, and that gives me the chi-squared for each of the data points. In some places it's bigger, so with this number point for x equals 9, it's fairly big because it's far off the line, but for the final point it's closer, so it's a smaller contribution. Then finally, we want the total of all these individual chi-squareds. How is the fit as a whole? So I click on cell E16, and I can go up here to the upper right of the screen where it says AutoSum, and it will say, oh, do you want to add up all these numbers? And you hit enter and say sure. So that is our total chi-squared, about 6,900. The game then the game then is to try and make this chi-squared number as small as possible. Okay, I can fumble around a little. For instance, maybe I decide that the parameter a could be a little bit bigger. So maybe I'll change that from 0.6 to 0.65. Let's see what happens. Remember, this chi-squared is around 6,900 right now. So I make that change, hit enter, and now this chi-squared is about 13,000. So that has made it a lot worse, and I think you can see in the graph that it has gotten worse. A lot of these points are further off than they were. So I will undo that change. So maybe it wants to be, say, 0.55. Okay, remember it's 6,900 to start with. Now it's gone to 13,000, so that was an equally bad change. So you could fumble around like this for quite a while. Maybe 0.6 was a good bet, or maybe I want to go to 0.58. Okay, remember it was 9,000. Now I've got it down to a little under 8,000, so that was a small improvement. So you could keep doing this. Or you could, after you've done this a little bit, it's time to say, okay, let's let the computer do the hard work. So, if you go over here to the Data tab, the written instructions tell you to look for the Analysis group and the Solve in icon, which would be over here. In all likelihood, your Excel does not have that icon. Fortunately, that's easy to fix. If you do have the icon, then you can ignore what I'm going to say for the next couple minutes. Go over to the File tab, down to Options on the left here. Window pops up. On the left, go to Add-ins. On the bottom here, where it says Manage Excel Add-ins, click on Go. And then over here, add-ins available, solver add-in, click so there's a check mark next to it, and then click OK. And there it is. The analyze group has shown up, and there's the solver icon. So click on the solver icon. So what it will do is it will change certain parts of the spreadsheet to accomplish a certain goal. The goal we want to accomplish is to minimize the total chi-squared, which is in cell E16. So that is the objective, cell E16. So I'll click on E16 and it'll say OK. What do we want to do to E16? We want to minimize it. And what cells do we want to change to accomplish this? Now if I click on the little spreadsheet symbol here, I can select the two cells, B1 and B2, that contain the parameters little a and little b. Once I've done that, click on the little spreadsheet picture over here again. Now there's one thing you have to do. There's this little check mark next to make unconstrained variables non-negative. You need to uncheck that. Select a solving method. I'm not going to mess with that. I'm just going to click on solve. And it says, hey, solver has found a solution. Do you like it? And you can click OK. Do we like it? Well, it's a smaller chi-squared than we got on our own. Before it was 7,800, now it's about 6,800. It meets the eyeball fit. These blue dots are almost all on the blue line here. Then these would be the best parameters. So you write those down. Now I'm going to copy them over here as well, because I want a copy of them for what we're going to do next. So these then are the values of the parameter that provide the best fit for this function. Now, of course, there might be another function that fits better. You would check that by writing down this chi-squared, 6848, and then typing in a different function in column C, and then see what chi-squared that gives you after you go through this process. So it would give you a way of testing different functions, in addition to a way of finding the best fit for a particular function. And you can test it against any function that you can type in here. So a much wider range than you can get with an Excel built-in trend line. Okay, so the last thing then is, how do we find the uncertainty of these parameters? So I've copied over here the best value of the parameters. And the mathematics of the statistics is that if you change a parameter such that chi-squared gets bigger by 1, then you've accomplished your task. You've changed the parameter to equal its best value plus its uncertainty. So I'm going to copy down here the value, which is our best chi-squared. I'll select it, do a copy, and I'll click down here and I'll do a paste special. I just want to paste the value. Okay, that's just for my reference, because now this is telling me I want to be one more than that. So I actually want to be 6849. So I'll go ahead and just change that to 6849. That's my target. So again, I could fumble around a little. So maybe if A is 0.582, well, look at all those digits. So let's just change this to 0.583. That change was a little too small. I need a slightly bigger change to pull this off. So maybe if I make it 0.5835. Okay, well, that was too much. Okay, so again, I could fumble around and try and get to the point where this is 6849. I'm getting a little closer. So yeah, you could do that, or you could go back and use solver again. So now I'll go back to solver. Again, the objective is the total chi-squared in cell E16, but now I don't want to minimize it. I want it to reach a specific value, which is 6849. So I will select the radio button for value of, enter the number 6849. Now this time I don't want to change both little a and little b. I want to keep little b the same because I want to see what change in little a increases my chi-squared by 1. So I will just select that, and it will only change that one cell. Solve. And there it is. It got pretty close to 6849, so I'll click OK. And now the difference between this number and that number, that's my uncertainty. So my uncertainty equals the best value minus the value that increases chi-squared by 1. Okay, now uncertainty is actually a positive number, so I'll ignore the negative sign. So my value of A is 0.58259 plus or minus 0.0005. So I would actually round that to the first digit that doesn't have uncertainty, which is the 4th decimal place. So I would call that 0.5825. And I can do that here. Click on the cell, go in the Home tab, and I can knock down. And I'll do the same thing here. I will knock this down to one uncertain digit. So my best value of the parameter A is 0.5826 plus or minus 0.0005. Okay. Part of your assignment will be to do the same thing for the parameter B. Now before you do that, you'll want to reset parameter A to its best value. So if you click on the copy the best value here and move that back over, that'll put everything back where it was. And then you can set up solver so it will only change the cell B2 and increase cell E16 to 6849. That will be part of your homework.